Okay, well let's just start at the very beginning. How do we get a potential energy versus separation graph for this? You're not going to find a function for these two magnets. And nobody, even at the end of a multivariable calculus class, knows how to integrate the dipoles to get a theoretical model for these magnets. But, good heavens, can you hear that? Yeah, we got some big rodents coming in here. Actually, I should have told my wife not to sweep the kitchen floor. It's a tile floor. So I'll talk loud enough that you can hear me. She'll be done soon. Okay. Once she gets into housekeeping, doesn't matter what you tell her, it's going to happen the way it happens. And she's a good housekeeper. I help. You know, I shout encouragement. No, if that was all I do, I'd be bruised and bloody. Okay, well, okay, do the experiment. Okay, in the experiment, now I'm writing it briefly. Various separations, you release the car and see how far it goes along a level surface. Okay? You time the car as it comes to rest. To determine its acceleration. Use the acceleration and the mass of the car to find coefficient of friction. And actually, you don't need the car mass. It divides out. Okay? Use acceleration to find the coefficient of friction. And the car mass to find the work done by the frictional force, the non-conservative force. In other words, if you know UK, which you can find from the acceleration of the coasting car, and the mass of the car, you can find the force of friction, and you know how far it goes at different separations. So you know how much energy it took to coast against friction, so you know what the potential energy was. And then you infer potential energy versus separation. Okay, so that's your first step. Now that's on the video, the camera's working, so I'm going to get rid of it. But if you need that for reference, there you have it. And let me just quickly clear this. Now, that gets us our potential energy. So knowing the potential energy here, what happens between here and here? Okay, well, sorry, Wes?
It depends on if we have an angle or
Yeah, I was going to say, let's do the simple case where theta equals 0. Well, then the work done by the non-conservative force,
tilt the camera.
oh yeah, you're right, good, thank you. Okay, then the work done by your non-conservative force is negative the force of friction multiplied by L. Okay? So it's negative mu km times L. Along the path, and that's, you got a bigger path than just that, but just talk about the path from here to here. You know what the work done by non-conservative forces is. You know the change in potential energy equals, let's give it a name, here it is on the graph, if your separation is A sub 0, it makes sense to call this potential energy 0. So your change in potential energy is this. What's your final potential energy along here? Well, I think you can still see it. We assume it's negligible here, so it's going to be negative of your initial potential energy. Now keep in mind that I might or might not actually give you a graph. Matter of fact, I almost certainly won't give you the graph, but I might tell you what the potential energies are at a number of different separations so you can draw a curve and make estimates, okay? I might even give you raw data from a version of the experiment with this car. So you've got various ways that you can get that initial potential energy. Okay. You have your change in potential energy, and you have the fact that the work done by your non-conservative force, and I did double check your materials and they do use WNC, okay? Okay, that's your change in potential energy plus your change in kinetic energy, right? Now that's from here to here. Actually, we've got LVNC. We did that just a minute ago. So. So change in kinetic energy would be the negative of your change in potential energy plus the work done by your non-conservative force. Well, that equals your initial potential energy minus, and I had mu km here. Somebody should have called me on that. Mu kmg, mu k times the weight, times L. Okay? So, final kinetic energy minus initial kinetic energy Now there's something I wish I'd done, so I'm going to do it even though it'll be hard to read. That little subscript there is MAG for magnetic potential energy, because we're going to have a change in gravitational potential energy, and we don't want to confuse that with any other kind of potential energy. So I'm going to have to call that, I'll put a mag on it. Didn't have room for the mag, but it's there. Okay? So we'll put a mag down here. And a mag here. Indicate this. Okay, well, what's the initial kinetic energy? Yeah, it's at rest here before we release it. Clearly we're releasing this thing from rest, so that this initial kinetic energy is 0. Right here is an equation that we can easily solve for the final velocity. Okay? Well, what if theta isn't 0? If theta isn't 0, then your gravitational potential energy is going to change. And that's going to be equal to mgl sine theta. Now you're going to have to draw pictures and stuff. I'm asking you to do the details in this. Explain why that's mgl sine theta. Yeah, fairly easy. You can just do a triangle right here. The angle is going to be theta. Hypotenuse is going to be L. Okay. But
We have to add in the H as well here. Like when you
I'm
get,
sorry again, Wes?
as far as the gravitational, do we need to consider in the height as well on that? Like, because it's still kind of floating.
No, that we're just doing the phase from here to here.
Okay.
Okay.
All right.
So we might not even choose to use the potential energy change here. Okay? Now one other evil thing that I could have done is I could have just given you the speed when the thing hits here and not given you the horizontal range. Okay? So that's a little more evil than I'm likely to be on the exam, but again, you never know, you know. You never know what I might do, so you should be prepared to do that. But that's one that I wouldn't expect to have a high percentage of success on. Okay, a class at this level on that question. If this is MIT, yeah, that'd be automatic. Okay, I do think some of you could get it, but this isn't MIT. We're just trying to prepare you for Virginia Tech, which is not MIT. It's a darn good school. MIT's in a, yeah, they breathe different air up there. Yeah, we just can't, we can't shoot for that. Okay, as much as I'd love to, we can't do it. Okay, well, anyhow, there we have it. So that's your first phase of motion. Okay? You can get what you need, which is the velocity at this point, and then you're down to the projectile. So you see, each of these is relatively simple. Okay? This is relatively simple. It's a little more complicated if you get that gravitational potential energy thing. And then you got to worry about, well, that changes some of what you did up here. I'm going to let you worry about that. Okay? But it does change your potential energy difference between here and here, because you now have a potential energy loss from the magnet and a potential energy loss from the change in elevation. And there's of course nothing to say that this angle theta has to be below horizontal. It could be above horizontal. Okay? You know, the projectile problems set up the same, makes no difference. As long as you get enough energy here to get to here, you got a projectile problem. Okay, well, we'll go on in a minute. I want to pause the camera.